July 20th, 1960, 31 degrees 28 minutes north, 80 degrees 33 minutes west, 30 miles off Cape Canaveral, Florida, 130 feet beneath the Atlantic surface. Commander James B. Osborne steadied himself against the periscope housing as the USS George Washington rolled gently in the current. The submarine's control room hummed with the muted whir of ventilation systems and the periodic ping of sonar. Around him, 23 officers and enlisted men stood at their stations, eyes fixed on instruments, hands hovering over controls they'd rehearsed 1,000 times but never executed for real. "Depth steady at 130 feet, sir," the diving officer reported, his voice carefully neutral despite the sweat beading at his temples. Osborne checked his watch. 1,205 hours, 5 minutes to launch window. He turned to the fire control station, where Lieutenant Commander Robert Wertheim sat before a console that looked like something from a science fiction movie fiction film. Rows of switches, dials, and indicator lights that had been installed just 8 months earlier. The George Washington was the first submarine in history designed to carry and fire ballistic missiles while submerged. 16 Polaris. One missile sat in vertical tubes behind the control room, each one a 30-foot, 14-ton package of solid rocket fuel and nuclear warhead. "Status on Tube 1, Osborne said. Wertheim's fingers moved across the console, checking readings. Missile pressurized. Guidance system initialized. Fire control solution locked. Tube hatch indicates sealed. He paused, then added what everyone in the room was thinking. "All systems show green, sir. But we won't know if it'll work until we try." If it'll work. That uncertainty hung in the recycled air like smoke. For the past 5 years, the best minds in American naval engineering had insisted that what they were about to attempt was not only possible but necessary for national survival. For just as long, Soviet engineers, men who'd put the first satellite into orbit and built the world's largest submarines, had been telling their superiors that launching a ballistic missile from beneath the ocean's surface was a physical impossibility. The Soviets had done the math. The water pressure alone at launch depth would crush any ignition system. Even if you could somehow light a rocket motor underwater, the massive drag forces would tear the missile apart or send it tumbling uselessly. The guidance systems would be scrambled by the turbulence. The submarine itself might be destroyed by the exhaust or the pressure differential. No, the Soviet admirals had concluded with certainty, submarine-launched ballistic missiles were a technological dead end, an American fantasy born of desperation. Osborne had read the intelligence reports containing these assessments. They'd been briefed to him and his crew as both warning and motivation. The entire Polaris program, billions of dollars, thousands of personnel, the reputations of admirals and politicians, rested on proving the Soviets wrong. "Sonar, any contacts?" Osborne asked. "Negative, sir. Nearest surface contact is 14 miles northeast. We're alone out here." Not quite alone. Osborne knew that somewhere above them, invisible beyond the hull, a small fleet of Navy vessels had established a security perimeter. Tracking stations along the coast were manned and waiting. At the Pentagon, at the White House, in offices throughout Washington, men were watching clocks and waiting for word. And further away, in Moscow, in Leningrad, in the closed cities of the Soviet military-industrial complex, other men were waiting too, certain they would hear news of an American failure. "Communications, send the ready signal," Osborne ordered. The radio operator tapped out the coded message that would inform the chain of command. George Washington was in position and prepared to make history or humiliation. The reply came back 90 seconds later, 6 words that had never before been spoken in any submarine. "You are authorized to launch missile." Osborne felt his heartbeat accelerate despite years of training in command composure. He looked around the control room one final time. These men, most of them in their 20s, some barely old enough to vote, were about to attempt something that violated common sense, that contradicted expert opinion, that seemed to defy physics itself. "Lieutenant Commander Wertheim," Osborne said, his voice carrying through the hushed space, "prepare to fire Tube 1. Wertheim's hand moved to a red guard cover marked Missile Launch Enable. He flipped it up, revealing a black switch beneath. "Tube 1 ready for firing sequence, sir." Osborne took a breath. The ocean pressed against the hull with millions of pounds of force. Above them, the surface world continued oblivious. Fishermen checking lines, tourists sunning on beaches, children building sandcastles. None of them knew that in the next 60 seconds, the rules of warfare, the balance of nuclear terror, and the trajectory of the Cold War were all about to change. Fire Tube 1.
The propellant-to-payload ratio must be precise for orbital insertion. This diagram illustrates the necessary thrust vectoring.
18 months earlier, January 14, 1959, Leningrad, Soviet Union. Admiral Sergei Gorshkov stood before a chalkboard covered in equations, his breath forming small clouds in the unheated conference room of the Naval Design Bureau. Outside, snow fell across the Neva River, muffling the sounds of the city. Inside, 6 of the Soviet Union's most accomplished naval engineers sat around a table littered with technical drawings, slide rules, and half-empty glasses of tea that had long since gone cold. "Show me again," Gorshkov said, pointing to a diagram of a submerged submarine with a missile tube. "Explain why the Americans cannot succeed." Pyotr Ivanovich Kovalev, chief designer at TSKB-16, the bureau responsible for Soviet submarine development, stood and approached the board. At 53, Kovalev had designed everything from midget submarines to the massive Project 611 attack boats. He'd studied at the Dzerzhinsky Naval Engineering Academy, survived Stalin's purges, and earned 3 orders of Lenin for his contributions to Soviet naval power. When he spoke about submarines, admirals listened. "Comrade Admiral, the problem is not one of engineering ingenuity, it is one of fundamental physics." Kovalev picked up a piece of chalk and began sketching. At 100 meters depth, the water pressure is approximately 10 atmospheres, 10 kilograms per square centimeter. To launch a missile, you must first equalize pressure in the launch tube with external water pressure, or the tube will implode when you open it. He drew a cylindrical tube inside a submarine hull, but here is the impossibility. To ignite a rocket motor, you need oxygen. Underwater, there is no oxygen. The Americans claim they will use solid fuel rockets, yes? He looked at his colleagues, who nodded. Solid fuel requires no external oxygen. It carries its oxidizer internally. Clever, but this creates a new problem. Kovalev drew flames erupting from the bottom of his sketched missile. The instant you ignite this motor inside a water-filled tube, you create explosive expansion of gases, thousands of degrees of heat, massive pressure. The water above the missile will resist this pressure. The submarine will experience forces equivalent to... He paused to calculate. Perhaps 100 tons of instantaneous thrust transmitted through the hull structure. This will buckle the pressure hull. It will shear mounting points. At minimum, it will damage the submarine's ability to dive safely. At worst, it will break the boat in half. One of the younger engineers, a man named Dmitry Ustinov, raised his hand tentatively. What if they use compressed air to push the missile out first, then ignite it above the surface? Impossible for multiple reasons, Kovalev responded immediately, warming to his subject. First, the compressed air required to overcome water pressure and missile weight would require storage tanks larger than the submarine itself. Second, and this is critical, even if you could eject the missile, it emerges into a chaotic, turbulent environment. He drew wavy lines around the missile. The submarine is moving, even if slowly. Ocean currents exist at all depths. The missile breaks the surface, not in calm air, but through violent water turbulence. It is tumbling, spinning. Its guidance system, sensitive gyroscopes and accelerometers are being subjected to random forces. How can it stabilize? How can it know which direction is up? By the time the guidance system orients itself, the missile has fallen back into the ocean or tumbled into a catastrophic trajectory. Another engineer, Viktor Makiev, head of the OKB-52 Design Bureau, added his voice. "We have analyzed the American Polaris specifications obtained through our intelligence services. The missile is relatively small, only 14 tons, perhaps 9 meters in length. This tells us they are compromising on range and payload to make it fit in a submarine. But small size creates its own problems." Makiev pulled out a document stamped with red security classifications. A small missile has less structural strength, less tolerance for the stresses of underwater launch. The Americans are attempting to fit a sophisticated guidance system, a nuclear warhead, and sufficient fuel for 1,200 nautical miles of range into this compact package. Each system must survive not only the launch stresses, but also months underwater in a confined, humid environment. The electronics alone. He shook his head. We cannot keep electronics functioning reliably in our submarines for more than a few weeks. They expect theirs to work after 6 months submerged. Gorshkov had been listening intently, his face impassive. As Commander-in-Chief of the Soviet Navy, he needed to understand not just whether something was possible, but whether Soviet resources should be devoted to pursuing it. The Americans claimed they would have an operational submarine-launched ballistic missile, what they called the Polaris, by 1960. The implications were staggering. A submarine armed with nuclear-tipped missiles could lurk anywhere in the world's oceans, virtually undetectable, capable of striking Soviet cities with no warning. It would make America's Strategic Air Command bombers, which Soviet air defenses were increasingly capable of intercepting, obsolete. It would shift the entire balance of nuclear deterrence, but only if it worked. What about their test program? Gorshkov asked. What have they actually achieved? Kovalev consulted another file. They have successfully launched prototype missiles from surface ships and from submarines at the surface. In September 1958, they launched a Polaris from a fixed platform at Cape Canaveral that flew 1,100 kilometers. Impressive, but these are controlled conditions. Calm weather, stable platforms, unlimited preparation time. And underwater tests? None that we know of, Comrade Admiral. There are rumors of small-scale experiments, but no confirmed underwater launches of a full-size missile. This is significant. If they had succeeded even once, American propaganda would be broadcasting it to the world. Their silence suggests they are encountering the same problems our analysis predicts. Gorshkov walked to the window and looked out at the snow-covered city. Leningrad had survived 900 days of Nazi siege, had starved and frozen and fought, and had endured. The Soviet Union had emerged from the Great Patriotic War as a superpower, had built nuclear weapons, had launched Sputnik into orbit before the Americans. Soviet engineers were not inferior to their Western counterparts. Often they were superior, forced to innovate despite limited resources. If underwater missile launches were truly impossible, the Americans would fail. Their admirals would be embarrassed, their program cancelled, their billions of dollars wasted. The Soviet Navy could focus on more practical weapons. Cruise missiles launched from the surface, mines, torpedoes, the massive submarine fleet that was already giving NATO nightmares. But if the Americans succeeded— Continue your analysis, Gorshkov said, turning back to the room. I want a complete technical assessment on my desk within 1 month. Include every reason why underwater launches cannot work. But also, he paused, his eyes hard, include preliminary designs for how we would accomplish it if, hypothetically, the laws of physics could be overcome. The engineers exchanged glances. They understood. Officially, submarine-launched ballistic missiles were impossible. Unofficially, the Soviet Union could not afford to be proven wrong.
To the Commissar. We've received new intelligence. Prepare the fleet for immediate deployment.
4 years earlier, November 17, 1955, the Pentagon, Arlington, Virginia. Admiral Arleigh Burke sat in his office on the 4th floor of the Pentagon, reading a report that would have seemed like science fiction to most naval officers. Outside, Washington was settling into an early winter evening, streetlights flickering on across the Potomac. Inside, Burke, newly appointed Chief of Naval Operations, the Navy's highest uniformed position, was contemplating a gamble that would either secure American security for decades or destroy his career. The report was marked top secret and bore the title Fleet Ballistic Missile System Feasibility Study. Burke had commissioned it 6 months earlier, driven by a gnawing certainty that the Navy was about to become obsolete. The Strategic Air Command had its bombers, massive B-52s that could reach any target in the Soviet Union. The Army was developing intermediate-range ballistic missiles that could be stationed in Europe and Turkey. But the Navy? Aircraft carriers were vulnerable to Soviet submarines. Surface ships could be tracked and targeted. Even submarines, the Navy's most survivable asset, were limited to torpedoes and short-range cruise missiles. In a nuclear war, the Navy would be largely irrelevant. Unless submarines could carry and launch ballistic missiles. Burke picked up his phone. "Get me Captain Levering Smith." 3 minutes later, Smith entered the office. At 45, Smith was one of the Navy's most brilliant technical minds, a Naval Academy graduate who'd earned a doctorate in physics from MIT and spent the war years developing fire control systems. Burke had personally selected him to head the Special Projects Office, a small organization tasked with developing what seemed impossible, a submarine-launched ballistic missile. "Captain Smith, I've read your report," Burke said, gesturing to a chair. "Tell me honestly, can we really do this?" Smith sat down, his expression serious. "Admiral, the honest answer is that we don't know yet. But the more important answer is that we have to try, because if we don't, someone else will." "The Soviets?" "Eventually, yes. But I'm more concerned about the Air Force." Smith leaned forward. "Right now, SAC controls the nuclear deterrent. They have the bombers. They're getting ICBMs. If the Navy can't field a credible strategic weapon, we become a sideshow, convoy escorts and coastal bombardment. The Air Force will argue correctly that they can do deterrence better and cheaper." Burke knew Smith was right. Inter-service rivalry was fierce in the defense establishment, and nuclear weapons were the currency of relevance. "Walk me through the technical challenges." Smith pulled a small notebook from his pocket. "The biggest problem is the missile itself. The Army's Jupiter missile, which we were originally supposed to use, is 60 feet long, weighs 110,000 pounds, and uses liquid fuel. You can't fit that in a submarine. Even if you could, liquid fuel is incredibly dangerous in a confined space. One leak, one spark, and you've got a fireball that would destroy the entire boat. So we need a different missile." "Correct. We need something smaller, lighter, and powered by solid fuel. Solid fuel is stable, can be stored for months, and doesn't need the complex fueling infrastructure that liquid rockets require." Smith flipped a page. "But here's the problem. No one has ever built a solid-fuel rocket powerful enough to carry a nuclear warhead 1,200 miles. The technology barely exists. We're essentially betting that we can develop an entirely new type of rocket motor. At the same time, we're designing submarines to launch it from." Burke stood and walked to a map of the world mounted on his wall. "What about the launch itself? Can you really fire a missile while submerged?" "That's the second major unknown," Smith admitted. "We've run calculations, built scale models, done tank tests. Theoretically, it's possible. We'd use compressed air to eject the missile from its tube, essentially blow it out like a cork from a bottle. The missile breaks the surface, clears the water, and then the solid fuel motor ignites. The submarine stays deep and moves away. Theoretically, yes, sir. Theoretically." Smith's voice carried the weight of uncertainty. "We won't know if it actually works until we try it with a full-size missile from an actual submarine. And if something goes wrong, if the missile tumbles, if the motor ignites too early, if the ejection system fails, we could lose the submarine and its entire crew." Burke returned to his desk. He'd commanded destroyers in the Pacific during the war, had fought at Leyte Gulf and Okinawa, had seen men die when technology failed or luck ran out. What Smith was proposing would put dozens of sailors at risk on an experimental platform attempting an unprecedented operation. But the alternative was worse. "What do you need?" Burke asked. "First, a decision on solid versus liquid fuel. If we commit to solid fuel, we need to bring Lockheed and Aerojet on board immediately. Second, we need electric boat to start designing a submarine that can accommodate vertical launch tubes. Third, and this is critical, we need political protection." "From whom?" "From everyone, sir. The Air Force will oppose this program because it threatens their budget. The Army will oppose it because we're abandoning their Jupiter missile. Congress will oppose it because it's expensive and risky. Even parts of our own Navy will oppose it because every dollar spent on Polaris is a dollar not spent on carriers and cruisers." Burke nodded slowly. Smith was describing a bureaucratic nightmare that would make the technical challenges seem simple by comparison. "I'll handle the politics. You focus on making it work." Smith stood to leave, then paused. "Admiral, there's one more thing. The Soviets are ahead of us in missile technology. They'll put a satellite into orbit before we do, maybe in the next year or two. When that happens, there'll be panic in Washington. Everyone will demand that we catch up, that we prove American technology is still superior. That political pressure could help us, or it could force us to rush, to cut corners, to launch before we're ready." "Then we'd better be ready," Burke said, 14 months later, October 5, 1957. The same office. Burke stared at the newspaper on his desk. The headline screamed across the front page, "Soviet satellite circling Earth, beeps picked up by US receivers." Sputnik. The Soviets had done it. A 184-pound metal sphere was orbiting overhead every 96 minutes, broadcasting its triumphant beep to the world below. American newspapers were calling it a humiliation, a disaster, proof that Soviet science had surpassed American capability. In living rooms across the country, families looked at the night sky with new fear, wondering if the same rockets that put Sputnik in orbit could deliver nuclear warheads to American cities. The phone on Burke's desk rang constantly. Congressmen demanding explanations, admirals proposing crash programs, journalists seeking comment. Burke ignored most of the calls. He was focused on one thing. Sputnik had just given him the political leverage he needed. Within 3 days, President Eisenhower called an emergency meeting of the National Security Council. Within a week, Congress was promising unlimited funds for missile development. Within a month, Burke had secured approval for an accelerated Polaris program. 18 submarines to be built on a crash schedule, with the first boat operational by 1960. It was insanely ambitious. Lockheed was still designing the missile. Electric Boat was still designing the submarine. The navigation systems that would allow a submerged submarine to know its exact position, essential for aiming missiles accurately, didn't exist yet. Neither did the fire control systems, the communication systems, or the specialized equipment needed to maintain nuclear weapons at sea for months at a time. But Burke had his authorization, his funding, and his political protection. The Navy's Special Projects Office ballooned from a staff of dozens to thousands. Contractors across the country began working on pieces of a puzzle that no one had assembled before. Captain Levering Smith, now promoted to Rear Admiral and given command of the entire program, moved his operation to a secure facility in the Pentagon's basement. His team worked around the clock, coordinating with dozens of contractors, solving hundreds of technical problems, pushing the boundaries of what was possible. They called it the Fleet Ballistic Missile Program. The missile itself was named Polaris after the North Star, a beacon of navigation, a symbol of constancy in an uncertain world. And now Admiral Smith had just told Burke that they were ready for the ultimate test. March 23, 1958. Sunnyvale, California. The explosion rattled windows 3 miles away. Inside the test bunker at Lockheed's Missile Systems Division, engineers watched through reinforced glass as a fireball consumed their test stand. The solid fuel motor, designated A1X-7, the 7th prototype in the Polaris development program, had burned for exactly 4.3 seconds before catastrophically disintegrating. Chunks of metal and composite material rained down across the test range, starting small brush fires that crash crews were already racing to extinguish. Dr. William Raborn, director of the Polaris program, stood motionless as acrid smoke drifted across the facility. Around him, engineers were already reviewing telemetry data, trying to understand what had gone wrong. This was the third motor failure in as many months. "Combustion instability," announced James Ivers, Lockheed's chief propulsion engineer, studying oscilloscope traces. "Look at this. Pressure spikes at 180 milliseconds, then harmonic resonance building until structural failure, the same pattern we saw in A1X-5. Rayborn moved closer to examine the data. The solid fuel motor was the heart of the Polaris missile, and it remained their biggest unsolved problem. Unlike liquid fuel rockets, which could be throttled and controlled, solid fuel motors were essentially controlled explosions. Once lit, they burned until the fuel was exhausted. The fuel itself was a carefully mixed combination of ammonium perchlorate oxidizer and polybutadiene rubber, packed into the motor casing under tremendous pressure. Get the mixture wrong, get the grain geometry wrong, get the casing thickness wrong, and the motor would either fail to produce enough thrust or, as they'd just witnessed, tear itself apart. "How many test units do we have left?" Rayborn asked. "4," Ivers replied, "and we're 6 weeks from the next production batch." 6 weeks, Rayborn calculated quickly. Admiral Burke wanted the first missile ready for testing by September, 5 months away. They needed working motors for submarine integration tests, for guidance system validation, for a dozen other critical milestones. Every failure pushed the schedule back, and the schedule was already impossibly tight. "Double the sensor array on the next test," Rayborn ordered. "I want pressure measurements every centimeter of that motor casing. I want high-speed cameras at 10,000 frames per second. We need to see exactly where the instability begins." As engineers dispersed to prepare for the next test, Rayborn walked outside into the California sunshine. The test stand was still smoking, fire crews hosing down hot metal. 3 years of his life had gone into Polaris. 3 years of 18-hour days, impossible deadlines, and technical challenges that would have seemed insurmountable to any rational person. But Rayborn wasn't rational about Polaris. He was obsessed. 600 miles north, Mare Island Naval Shipyard, Vallejo, California. Commander Robert Weeks stood in what would become the missile compartment of the USS George Washington and tried to imagine 16 Polaris missiles standing vertically behind him. It required a considerable act of imagination, because currently he was standing in an empty space that smelled of fresh-cut steel and welding fumes. The George Washington had started life as something else entirely. SSN 598, a skipjack-class attack submarine being built by Electric Boat in Groton, Connecticut. Then Admiral Burke's accelerated schedule had intervened. Rather than design and build a ballistic missile submarine from scratch, a process that would take years, the Navy had made a radical decision. They would cut an existing submarine in half and insert a new 130-foot section containing missile tubes. The George Washington had been sliced apart, like a loaf of bread, her forward and aft sections separated. Now a massive new compartment was being fabricated, a steel cylinder 33 feet in diameter, containing 16 vertical tubes, each 28 feet tall and wide enough to accommodate a Polaris missile. The tubes were arranged in 2 rows of 8, their tops sealed by hatches that would open to the ocean above. The engineering was brutally complex. Each tube had to withstand full ocean pressure, had to be perfectly aligned for vertical launch, had to have its own gas generator system for missile ejection, and had to integrate with fire control systems that were still being designed. Commander Weeks, a civilian engineer named Martin Peterson, approached, carrying blueprints that were already covered in revision marks. "We've got a problem with the tube hatches." Weeks had heard those words at least twice a day for the past 4 months. "Show me." Peterson spread the blueprints across a makeshift table. "The hatches need to open against full sea pressure, about 60 pounds per square inch at launch depth. We've designed hydraulic rams powerful enough to do that. But there's a timing problem. If a hatch opens too slowly, water floods into the tube before the missile can be ejected. If it opens too fast, the sudden pressure release creates a shockwave that could damage the missile or its guidance system." What's Lockheed saying? They want the hatch open in 0.3 seconds. Electric Boat says that's mechanically impossible with hatches this size. We'd need hydraulic systems that would add 2 tons per tube. The submarine's weight budget is already exceeded. Weeks stared at the blueprints. Every system on the George Washington was pushing the limits of what was possible. The navigation system, a ship's inertial navigation system, or SINS, used gyroscopes so sensitive they could detect the rotation of the Earth, allowing the submarine to know its position within a few hundred yards without surfacing. The fire control system required computers that could calculate missile trajectories while accounting for the submarine's depth, speed, and attitude. The communication system needed to receive encrypted messages while the submarine remained deep enough to be safe from detection. And none of it would matter if they couldn't physically launch the missiles. Get representatives from Lockheed, Electric Boat, and the Bureau of Ordnance in one room. Weeks ordered. Tomorrow morning, 0800. We're going to solve the hatch problem, or everyone stays until we do. June 15th, 1959. Cape Canaveral, Florida. The dawn sky was cloudless, perfect conditions for a test launch. Admiral Raborn stood on an observation platform 2 miles from Pad AE, where a Polaris A-1 missile sat gleaming white in the early light. This was Test Unit A1X-19, incorporating all the lessons learned from 18 previous tests, 3 explosions, and countless design modifications. If it worked, this missile would prove that the solid fuel motor problem was solved. If it failed, the entire Polaris program schedule would collapse. T-2 minutes, the launch controller announced over loudspeakers. Raborn raised binoculars, studying the missile. It looked impossibly slender, just 54 inches in diameter, 28 feet tall, sleek and purposeful. Inside that white shell was the culmination of years of work. A 2-stage solid fuel motor that would burn for approximately 60 seconds. A guidance system that would steer the missile to its target, and, in operational missiles, a thermonuclear warhead with a yield of 600 kilotons. T-1 minute. The observation platform was crowded with officers and civilians, Navy brass monitoring the test, contractors with their professional reputations on the line, Pentagon officials who controlled funding. Everyone was silent, watching the distant pad. T-30 seconds. Raborn's hands were steady on the binoculars, but his pulse was hammering. Every test was a referendum on whether Polaris was possible, whether the Navy had bet correctly, whether thousands of people were working towards something achievable or chasing an impossible dream. 10, 9, 8. The count reached 0. For a fraction of a second, nothing happened. Then white fire erupted from the missile's base, a roar that reached them as pressure wave and sound simultaneously. The Polaris lifted, slowly at first, fighting inertia and gravity, then faster as the motor reached full thrust. The exhaust plume was a brilliant white column of fire that seemed to tear a hole in the morning sky. 10 seconds. The missile was 1,000 feet up, accelerating hard. 20 seconds. 5,000 feet, the motor still burning perfectly. 30 seconds. The missile was a white dot against the blue, climbing on a pillar of flame. At 62 seconds, the first stage burned out and separated. A moment later, the second stage ignited. Another perfect burn. The missile arced eastward out over the Atlantic, accelerating to speeds that would have been incomprehensible to naval officers just a generation earlier. Telemetry confirms successful staging, the launch controller reported. Guidance is tracking nominal trajectory. We have a good flight. The missile disappeared into the distance, heading for a target area 1,100 miles downrange. Tracking stations would follow it all the way, radar and telemetry confirming that every system worked exactly as designed. On the observation platform, someone started clapping. Then everyone was applauding, shaking hands, grinning with relief and triumph. A 1X-19 had flown perfectly, proof that solid fuel motors could work, that the guidance systems could steer, that Polaris was real. Raborn allowed himself a small smile. One problem solved, 100 more to go. July 20th, 1960. USS George Washington, 130 feet beneath the Atlantic. Wertheim's finger hovered over the firing switch. Commencing launch sequence, he said, his voice steady despite the monumental nature of what was about to happen. He pressed the switch. Deep in the missile compartment, a series of events began that had been rehearsed in simulators but never executed for real with a live missile and a submerged submarine. First, the tube hatch hydraulics engaged, massive rams forcing the 2,000-pound hatch open against the crushing pressure of the ocean above. The hatch swung away in precisely 0.31 seconds, and seawater began flooding into Tube 1. Simultaneously, a gas generator at the bottom of the tube ignited. It was a solid fuel charge, not unlike a giant shotgun shell, designed to produce an enormous volume of high-pressure steam in a fraction of a second. The steam rushed upward through the water-filled tube, creating a bubble of pressure that would push the 14-ton missile toward the surface. In the control room, Osborne felt the deck shudder beneath his feet, a deep, primal vibration that traveled through the submarine's hull. Warning lights flickered briefly on the ballast control panel as the force of the gas generator translated into movement. Ejection sequence initiated, Wertheim reported, watching his instruments with absolute concentration. Tube pressure rising. 400 psi, 600 psi, 800 psi. The pressure was building faster than the water could be displaced, creating the exact conditions needed to launch the missile like a cork from a champagne bottle. But there was a razor-thin margin for error. Too much pressure and the tube could rupture, flooding the submarine. Too little and the missile would barely clear the surface, tumbling back into the ocean as a $13 million piece of floating debris. 1,000 psi, Wertheim continued. Missile ejection confirmed. I have separation. In the missile tube, the Polaris-designated PT-1, Polaris Test 1, was accelerating upward through the water-filled tube at nearly 30 feet per second. The missile's internal systems, gyroscopes, accelerometers, and guidance computers that had cost more than most Americans would earn in a lifetime, were being subjected to violent forces and random turbulence. Everything depended on whether those systems could maintain their orientation and function despite conditions no missile had ever experienced. Time to surface, Osborne asked. 4 seconds, someone calculated. 4 seconds. In that span of time, PT-1 was traveling through an environment that represented everything hostile to rocketry. The missile was heavy, blunt, and moving through a medium 800 times denser than air. Pressure on the nose cone was immense. The guidance system was tumbling through 3 axes simultaneously, struggling to maintain any sense of which way was up. If the missile emerged at the wrong angle, even a few degrees off vertical, it would either fall back into the ocean or fly on a catastrophic trajectory. Surface breach, the sonar operator called out. He was listening to the sounds transmitted through the water, and his instruments had just registered the distinctive acoustic signature of a large object breaking through the interface between ocean and air. In the control room, every man held his breath. This was the moment of truth. The missile was above the surface, but was it stable? Was it oriented correctly? Would the motor ignite? 130 feet above them, 12-10 hours. PT-1 burst through the Atlantic's surface in a geyser of white water and steam. For one heartbeat, the missile hung suspended, a white cylinder wreathed in spray, tilting slightly to port, its internal systems screaming electronic data as gyroscopes spun and computers calculated and gas jets fired in microsecond bursts to correct the trajectory. Then the solid fuel motor ignited. The first stage motor, the same design that had destroyed 3 test stands before engineers solved the combustion instability problem, roared to life with 60,000 pounds of thrust. Flame erupted from the missile's base, a white-hot column that vaporized seawater and created a roar audible for miles. PT-1 accelerated upward, climbing out of its own steam cloud, rising on a pillar of fire that stretched back to the ocean below. Aboard the observation ships stationed around the launch area, officers raised binoculars and tracking equipment locked on. Radar stations along the coast acquired the target, their screens showing a bright return climbing at an angle of 87 degrees. Nearly vertical, well within acceptable parameters. PT-1 climbed through 1,000 feet, 2,000 feet, 5,000 feet. The motor burned with mathematical precision, consuming fuel at a rate of 200 pounds per second, converting chemistry into velocity. The missile's guidance system, having survived the underwater launch and surface breakthrough, now functioned exactly as designed, making constant tiny adjustments to keep the missile on its programmed trajectory. At 40,000 feet, 61 seconds after ignition, the first stage burned out. Small explosive charges separated the spent motor casing, and the second stage ignited seamlessly. Another burst of thrust, another acceleration. PT-1 was now traveling at nearly 8,000 miles per hour, following a ballistic arc that would carry it 1,100 miles downrange to a target area near Grand Bahama Island. Aboard USS George Washington. SOCOM reports successful motor ignition, the communications officer announced, reading from a message just received from the surface command ship. Missile tracking nominal, flight path is good. The control room erupted. Men were shaking hands, clapping each other on the shoulders, grinning with relief and triumph that they were struggling to contain within military discipline. They had done it. The impossible thing, the thing Soviet engineers had declared could not be done, the thing that had consumed 5 years and billions of dollars, they had actually done it. Osborne allowed himself a brief smile, then restored order with a single gesture. "Gentlemen, that was Tube 1. We have 15 more to test." The celebration subsided, but the electricity in the air remained. "Diving officer, take us to 150 feet. Communications, send confirmation to ComSublant. Launch successful, preparing for second test. Lieutenant Commander Wertheim, prepare Tube 2 for launch in 30 minutes. The crew returned to their stations, but everything felt different now. They were no longer attempting something that might be impossible. They were operating a weapons system that had just proven itself. The USS George Washington had become what it was designed to be, a platform for delivering nuclear weapons from a location that no enemy could predict or defend against. Over the next 4 hours, the George Washington fired 15 more Polaris missiles. Not all of them performed perfectly. PT-4 experienced guidance system problems and tumbled off course after second-stage ignition. PT-9 had a partial first-stage failure that resulted in reduced range. But the fundamental concept was proven. Missiles could be launched from beneath the ocean. Submarines could carry and fire ballistic weapons. The strategic calculus of nuclear warfare had just fundamentally changed. 1,700 miles away, the Pentagon, Admiral Arleigh Burke received the flash message at 12:47 hours. George Washington reports, successful launch Polaris missile from submerged position. Repeat, successful submerged launch. Burke read the message 3 times, ensuring he understood every word correctly. Then he picked up his phone and asked to be connected to the White House. President Eisenhower needed to know immediately. While waiting for the connection, Burke walked to his office window and looked out over the Potomac. 5 years ago, when he'd authorized Captain Smith to begin the Polaris program, the Soviet Union had seemed to be winning the Cold War. Their missiles were more powerful, their satellites were flying overhead, their submarines were multiplying faster than NATO could track them. The nuclear balance had seemed to be tipping toward Moscow. Now, in the space of 4 hours off the coast of Florida, that balance had shifted. A submarine was almost impossible to track. It made no radar signature, left no contrails, operated in an environment where even the most sophisticated sensors struggled to detect it. The George Washington could disappear into the Atlantic, patrol for months, move thousands of miles, and surface anywhere to fire its missiles, giving the United States a nuclear deterrent that was essentially invulnerable to first strike. The Soviets could destroy every strategic air command base, could obliterate every ICBM silo, could eliminate every bomber before it got airborne, but they could not find and destroy submarines hidden in the vastness of the world's oceans, which meant they could not eliminate America's ability to retaliate, which meant, if deterrence theory held, they would never attempt a first strike at all. Mutual assured destruction had just become truly mutual and truly assured. "Mr. President," Burke said when Eisenhower came on the line, "I have something to report."
They know. Get out now!
July 21st, 1960, Moscow, Soviet Union. 0400 hours local time. The phone beside Colonel General Sergei Biryuzov's bed rang with the harsh insistence that meant only one thing: urgent intelligence that could not wait for morning. Biryuzov, commander of the strategic rocket forces, reached for the receiver while his mind was still struggling out of sleep. "Comrade General, you need to come to headquarters immediately," said the voice of his deputy, Major General Konstantin Moskalenko. There was something in Moskalenko's tone, not quite panic but close, that brought Biryuzov fully awake. "What's happened?" "The Americans have launched ballistic missiles from a submarine. Multiple launches. All successful." Biryuzov was silent for 3 seconds, his mind racing through implications. "I'll be there in 20 minutes. He dressed quickly, not bothering to wake his wife. A staff car was already waiting outside his apartment building, engine running. The streets of Moscow were empty at this hour, and the driver made the trip to Strategic Rocket Forces headquarters in just 14 minutes. The operations center was fully lit despite the hour, crowded with officers and intelligence analysts. Maps covered the walls, teletype machines chattered with incoming reports, and at the center of it all stood Moskalenko, surrounded by documents marked with the highest security classifications. "Show me everything," Biryuzov ordered. Moskalenko gestured to a map of the Atlantic Ocean marked with annotations. At approximately 1700 hours yesterday, Moscow time, the American submarine USS George Washington conducted 16 test launches of Polaris missiles while submerged off their coast of Florida. Our signals intelligence station in Cuba intercepted communications between the submarine and surface vessels. Our naval attaché in Washington has confirmed through secondary sources that the tests occurred. 16 launches. Biryuzov's voice was carefully controlled, but his mind was reeling. 16 successful launches meant this was not a lucky accident or a single prototype demonstration. This was an operational weapons system. Yes, Comrade General, 14 missiles flew their full programmed trajectories, approximately 1,800 kilometers. 2 experienced malfunctions, but still launched successfully from underwater. The Americans are characterizing the test as completely successful. Biryuzov moved to the map and studied the markings. The implications were cascading through his strategic calculations like dominoes falling. How many of these submarines do they have? Intelligence estimates 5 will be operational by the end of 1960. The Americans have announced plans to build a total of 41. 41. Biryuzov did the arithmetic quickly. If each submarine carried 16 missiles, that was 656 ballistic missiles that could be launched from positions anywhere in the world's oceans. Missiles that could reach Moscow, Leningrad, Kiev, every major Soviet city. Missiles launched from platforms that Soviet anti-submarine forces had virtually no ability to track or destroy. Has this been reported to Comrade Khrushchev? Marshal Malinovsky is briefing him now. Biryuzov walked to a detailed map of the Soviet Union's defensive systems. Radar installations, missile batteries, airfields with interceptor aircraft. Every one of these systems was designed to defend against bombers and land-based missiles. None of them could do anything about missiles launched from submarines that could be positioned 200 miles off the Soviet coast, giving just 5 minutes warning before impact. "Get me Admiral Gorshkov," Biryuzov ordered, "and find Kovalev, wake him up if necessary. I want every engineer who told us this was impossible in a conference room by 0800 hours. 0847 hours. Naval Design Bureau, Leningrad." Pyotr Kovalev stood before the same chalkboard where, 18 months earlier, he had explained to Admiral Gorshkov why underwater missile launches were physically impossible. Now he was erasing those equations, his hand moving mechanically while his mind struggled to accept reality. The Americans had done it. Everything he had said was impossible: igniting motors underwater, stabilizing missiles through the turbulent surface interface, maintaining guidance system functionality. The Americans had somehow solved all of it. Behind him, the same group of engineers sat around the same table, but the atmosphere was entirely different. Before, they had been confident, even dismissive of American ambitions. Now they were silent, shocked, confronting the uncomfortable truth that they had been wrong. "Comrades," Kovalev began, his voice heavy, "we have been presented with intelligence regarding the American Polaris system. I will be direct. Everything we believed about the impossibility of underwater missile launches was incorrect." He turned to the chalkboard and began sketching quickly. The Americans solved the problems through methods we did not anticipate. First, they abandoned liquid fuel entirely and developed solid fuel motors with thrust-to-weight ratios superior to anything we currently possess. Second, they use compressed air ejection to push the missile clear of the water before motor ignition, eliminating the problem of igniting underwater. "But the structural forces," one engineer began, "they strengthened the submarine hull with new welding techniques and structural supports. They accepted a weight penalty we were unwilling to consider." Kovalev's voice carried a note of grudging respect. Third, and most importantly, they developed miniaturized guidance systems that can withstand the launch stresses. Our own guidance systems are too large, too fragile. The Americans have surpassed us in electronics integration. Victor McCabe, the designer who had been so confident about American failures, spoke up. What about the missile's accuracy? Range? Payload? Kovalev consulted a classified intelligence summary. Estimated range, 2,200 kilometers. Circular error probable, approximately 900 meters. Payload, single warhead, estimated yield 600 kilotons. These specifications are inferior to our R-7 or R-12 missiles, but they are entirely adequate for strategic purposes. A 600 kiloton warhead does not need to be accurate when targeting a city. The room was silent as the engineers absorbed this information. They had been beaten not by superior physics, but by superior engineering, by American willingness to accept compromises, to think differently about the problem, to invest resources at a scale the Soviet Union had not matched. What are our orders? McCabe asked. Marshal Malinovsky has directed that we develop a Soviet submarine-launched ballistic missile capability within 3 years, Kovalev replied. We are to have a working system by 1963. 3 years. It had taken the Americans 5 years, with unlimited funding, access to the world's most advanced electronics industry, and a head start in submarine technology. The Soviet Union would have to accomplish the same thing in less time, with fewer resources, starting from behind. But it was not impossible. The Americans had proven that. July 23, 1960. The White House, Washington, D.C. President Eisenhower stood before a wall map in the cabinet room, listening as Admiral Burke described the strategic implications of the Polaris tests. Secretary of Defense Thomas Gates was present, along with Alan Dulles of the CIA and several senior military officers. Mr. President, what we've achieved fundamentally changes the nuclear balance, Burke was saying. The Soviets have more ICBMs than we do, and their missiles are more powerful. But ICBMs are fixed in silos. The Soviets know where ours are, and we know where theirs are. They can be targeted, destroyed in a first strike. Burke moved to the map, gesturing to the world's oceans. But a submarine at sea is essentially invisible. Even with all their resources, the Soviets cannot track more than a tiny fraction of our submarine fleet at any given time, which means they cannot eliminate our retaliatory capability even if they achieve complete surprise in a first strike. Eisenhower, who had commanded millions of men in World War II and understood military strategy at the deepest level, nodded slowly. You're saying Polaris makes our deterrent credible. More than credible, Mr. President, invulnerable. As long as we have submarines at sea carrying Polaris missiles, the Soviets know with absolute certainty that any attack on the United States will result in devastating retaliation. This removes any incentive for them to strike first. Alan Dulles spoke up. Our intelligence indicates the Soviets are already scrambling to develop their own submarine-launched missiles. Khrushchev has reportedly ordered a crash program. Let them scramble, Burke said. We have a 5-year head start, and we're accelerating production. By 1965, we'll have 35 Polaris submarines operational, 560 missiles that can strike from positions the Soviets cannot predict or defend against. Eisenhower walked to the window, looking out over the South Lawn. He had spent his presidency trying to avoid nuclear war while maintaining American security. He had approved U-2 flights over the Soviet Union, had authorized the development of ICBMs, had watched with alarm as the Soviets put satellites into orbit and developed increasingly powerful missiles. The nuclear arms race had seemed endless, an ever-escalating competition with no clear endpoint. But perhaps Polaris changed that calculus. If both sides possessed invulnerable second strike capabilities, if neither side could achieve victory through a surprise attack, then perhaps the arms race would stabilize. Perhaps mutual deterrence would become mutual survival. Admiral Burke, Eisenhower said, turning from the window, I want you to accelerate the Polaris program. Whatever resources you need, you'll have them. I want submarines on patrol in the Atlantic, the Pacific, and the Mediterranean within a year. Yes, Mr. President. And Admiral, Eisenhower's expression was grave. Make certain these submarines never have to fire their missiles in anger. August 2nd, 1960, Pravda, Moscow. The headline appeared on page 3, buried beneath stories about agricultural production and a visit by Khrushchev to a tractor factory. American military conducts missile tests. The article was brief, just 4 paragraphs, acknowledging that the United States had tested submarine-launched missiles, but characterizing them as inferior weapons based on outdated technology that posed no threat to the peace-loving peoples of the Soviet Union. No Soviet citizen reading the article would have understood its real significance. But in intelligence agencies, military headquarters, and classified facilities across the Soviet Union, thousands of people were now working desperately to match what the Americans had achieved. The underwater arms race had begun October 15, 1960, Holy Loch, Scotland. A cold rain swept across the Scottish coast as the USS Patrick Henry, the second of the George Washington-class ballistic missile submarines, slid into Holy Loch and dropped anchor. On the shore, a hastily constructed tender facility, little more than reinforced docks and prefabricated buildings, waited to support America's first forward-deployed nuclear deterrent patrol. Commander Charles Pete Carlisle stood on the Patrick Henry's bridge, watching through binoculars as protesters gathered beyond the security perimeter. They carried signs reading, "Yankee go home," and "No nuclear weapons in Scotland." Local fishing boats had tried to block the submarine's approach until the Royal Navy escorted them away. The Cold War had arrived in Scotland, and not everyone was happy about it. But political protests meant nothing compared to the strategic reality. The Patrick Henry carried 16 Polaris A-1 missiles, each tipped with a nuclear warhead capable of reaching targets deep inside the Soviet Union. And unlike bombers that needed hours to reach their targets, unlike ICBMs that required minutes of preparation, the Patrick Henry's missiles could be launched in under 15 minutes from the moment the order was received. More importantly, the submarine could patrol undetected for 60 days at a time, surfacing only to receive encrypted communication signals, invisible to Soviet surveillance. Right now, at this very moment, 3 other Polaris submarines were on patrol in the Atlantic and Pacific. 12 more were in various stages of construction or testing. By 1963, Admiral Burke's plan called for 16 submarines on patrol simultaneously, providing a constant, invulnerable nuclear deterrent. "Sir, we've received orders to prepare for first deterrent patrol," the communications officer reported. "Departure date is October 22nd. Carlisle nodded. 7 days to load provisions, conduct final system checks, and brief the crew. Then the Patrick Henry would submerge, transit into the Atlantic, and take up a patrol station somewhere in the vast emptiness between Scotland and the Soviet Union. For 60 days, 130 men would operate in an underwater world of controlled temperature, recycled air, and the constant hum of machinery, carrying enough destructive power to obliterate a dozen cities. "Acknowledge the order," Carlisle said, "and tell the crew to ignore the protesters. They don't understand what we're preventing." November 3rd, 1960. Severodvinsk, Soviet Union. Snow was falling across the Sevmash shipyard when Admiral Gorshkov arrived to inspect the Soviet Union's response to Polaris. The submarine designated K-19, soon to be equipped with the new R-13 ballistic missiles, sat in dry dock, her hull painted in the red lead primer that preceded final construction. Gorshkov climbed down into the missile compartment where 3 vertical tubes were being installed. Not 16 like the American submarines, Soviet engineers had only managed to fit 3 tubes while maintaining the structural integrity necessary for deep diving. And the missiles themselves were larger, heavier, more temperamental than the solid-fuel Polaris. Pyotr Kovalev met him at the base of the missile tubes, wearing a heavy coat against the cold that penetrated the unfinished submarine. "Comrade Admiral, as you can see, construction is proceeding. We estimate completion by March 1961, with sea trials beginning in June." "And the missiles?" Gorshkov asked. Kovalev's expression tightened almost imperceptibly. "The R-13 is experiencing difficulties. The liquid fuel handling systems are proving more complex than anticipated in a submarine environment. We have had 3 accidents during fueling exercises." "What kind of accidents?" "Fuel leaks. In one case, a minor fire." No casualties, but the incidents have caused delays. Kovalev paused, choosing his words carefully. Comrade Admiral, I must be frank. The American approach of using solid fuel was correct. Our insistence on liquid fuel because of our existing expertise has created problems we did not anticipate. Liquid fuel requires complex pumping systems, temperature control, and handling procedures that are difficult to implement aboard a submarine. The Americans avoided all these problems by using solid fuel. Gorshkov was silent for a long moment, looking up at the partially installed missile tubes. The Soviet Union's first ballistic missile submarine would carry 3 missiles versus 16 for the Americans. Those missiles would be harder to maintain, more dangerous to handle, and less reliable. The submarine itself would be noisier, easier to detect, less capable of extended patrols. The Americans had not just beaten the Soviet Union to operational deployment, they had designed a fundamentally superior system. How long until we can develop solid fuel missiles comparable to Polaris? Gorshkov asked. 5 years, Comrade Admiral, perhaps more. We are essentially starting from the beginning with solid fuel technology. The Americans had a decade of work before Polaris. 5 years. By that time, the Americans would have 40 Polaris submarines operational, carrying 640 missiles. The Soviet Union would have perhaps a dozen boats, carrying 3 or 4 missiles each. The strategic imbalance would be overwhelming. Gorshkov had spent his career building the Soviet Navy into a force that could challenge American naval supremacy. He had overseen the construction of hundreds of submarines, the development of long-range cruise missiles, the creation of a fleet that made NATO planners lose sleep. But in one stroke, the Polaris program had rendered much of that investment obsolete. Submarines were now strategic weapons platforms first, and attack vessels second. The Navy that controlled submarine-launched ballistic missiles would dominate nuclear deterrence, and right now, that Navy was American. Continue the work, Gorshkov ordered. We will deploy what we can as quickly as we can, and inform the design bureaus that solid fuel missiles are now our highest priority. December 30th, 1960, the Pentagon. Admiral Arleigh Burke sat in his office on his last day as Chief of Naval Operations, reviewing a summary of the Polaris program he had championed 5 years earlier. The numbers were staggering. 5 submarines operational: George Washington, Patrick Henry, Theodore Roosevelt, Robert E. Lee, Abraham Lincoln. 11 more under construction, 80 successful missile launches from 92 attempts, an 87% success rate. 0 submarine losses, 0 casualties from the test program. Total cost, $3.2 billion, less than the Air Force had spent on the cancelled B-70 bomber program. But the real measure of success wasn't in the numbers. It was in the intelligence reports that crossed his desk daily, describing Soviet panic and scrambling, their desperate efforts to match a capability they had declared impossible just 2 years earlier. It was in the diplomatic communications showing that America's NATO allies now felt more secure, knowing that even if Soviet missiles destroyed every airbase in Europe, submarines in the Atlantic could still retaliate. It was in the calculations showing that the strategic balance, which had tilted dangerously toward the Soviet Union after Sputnik, had now stabilized. Burke's successor, Admiral George Anderson, entered the office carrying a bottle of bourbon and 2 glasses. "Thought you might want to toast your last day properly," Anderson said. Burke smiled and accepted a glass. "To Polaris." "To the men who made it possible," Anderson corrected. "Admiral Smith and his engineers, Commander Osborne and every submarine crew who trusted their lives to an untested system. The workers at Electric Boat and Lockheed who put in 18-hour days. And to you for having the vision to see what was necessary even when everyone said it was impossible." They drank, the bourbon burning pleasantly. "You know what the Soviets are calling it?" Anderson asked. "They have a saying now, the Americans made the ocean invisible. They're terrified of what they can't see, can't track, can't defend against." Burke walked to his window, looking out over the Potomac for the last time as CNO. 5 years ago, this view had seemed darker, more uncertain. The Soviet Union had appeared unstoppable. Larger armies, bigger missiles, successful satellite launches, while American rockets exploded on their pads. The psychological warfare of Khrushchev's boasts about burying the West had seemed almost credible. But now American submarines prowled the oceans with invulnerable nuclear arsenals. Now the Soviets were the ones playing catch-up, struggling to match American technology, watching their strategic advantage evaporate into the depths of the Atlantic and Pacific. "The ocean isn't invisible," Burke said quietly, "but what we put in it is." And that makes all the difference. May 10th, 1963, Atlantic Ocean, 200 miles east of Norfolk, Virginia. Lieutenant Commander Michael Barrow stood in the control room of the USS Sam Houston, the sixth boat of the Ethan Allen class, an improved version of the George Washington design. The Sam Houston was on patrol day 43 of a 60-day mission, carrying 16 Polaris A-2 missiles, an upgraded version with longer range and improved accuracy. The patrol had been uneventful, which was exactly the point. The submarine had departed Norfolk, transited to a classified patrol area in the North Atlantic, and spent 6 weeks moving slowly through the deep ocean, occasionally rising to periscope depth to receive encrypted communications, but otherwise invisible to the world above. "Sir, we've received a flash message," the communications officer reported. "Command directs us to proceed to secondary patrol station. Soviet submarine activity has increased in our primary area." Barrow studied the navigation chart. The secondary station was 300 miles northwest, 2 days transit at quiet speed. "Helm, come to course 315. Make your depth 400 feet. Ahead 1/3. The submarine turned silently, tilting slightly as the diving planes adjusted. Around Barrow, 140 men went about their duties, manning reactor controls, monitoring sonar, maintaining weapon systems, cooking meals in the cramped galley. They were all volunteers, all extensively trained, all trusted with the most powerful weapons in human history. And the Soviets had no idea where they were. That was the genius of Polaris, Barrow reflected. Not the missiles themselves, though they were impressive enough, but the platform. A submarine at sea was effectively invisible. Even with all their satellites, all their spy trawlers, all their sophisticated detection systems, the Soviets could only locate a tiny fraction of American submarines at any given time, which meant they could never execute a successful first strike because they could never eliminate the submarines that would retaliate. 3 years after the first underwater launches, Polaris had achieved what strategists called assured second strike capability. The term was dry, academic, but the reality was profound. Nuclear war had become unwinnable because neither side could prevent the other from retaliating. The missiles that Soviet engineers had deemed impossible had made mutual destruction truly mutual, truly assured. And in the strange logic of nuclear deterrence, that made the world safer. "Course 315, sir," the helmsman reported, "making for secondary patrol station." "Very well," Barrow acknowledged. The Sam Houston slipped through the dark Atlantic, carrying its terrible cargo, maintaining the peace through the threat of annihilation. It was a paradox that would have seemed insane to any previous generation of warriors. Weapons built never to be used, submarines on patrol to prevent war rather than fight it. But it worked, and it had all started with a single submarine, a single crew, and 16 launches that Soviet engineers had said were impossible. The Polaris program continued until 1996, when the last Polaris-equipped submarine was retired. By then, the concept pioneered by USS George Washington had evolved through multiple generations. Polaris gave way to Poseidon, then Trident, each generation more capable than the last. Today, submarine-launched ballistic missiles remain the most survivable leg of the nuclear triad. Still operating on the same principle proven off Cape Canaveral on July 20, 1960. What cannot be found cannot be destroyed. The Soviet Union eventually developed their own submarine-launched ballistic missiles, but never achieved the reliability, range, or stealth of their American counterparts. The gap created by Polaris was one the Soviet Navy never fully closed. In the end, the engineers who said it was impossible were proven wrong, not by theory, but by the roar of rockets rising from the ocean depths.